Assalamu alaikum everyone. This is lecture 4. We are still covering chapter 2. Basically in the last class we have seen how to obtain transfer function from the differential equation and vice versa, and also how to find out the system response from the transfer function. So the main objective of this chapter is to find out the mathematical modeling or transfer function in the frequency domain, that is applying the Laplace transformation. So on this, on the continuation, actually we'll start with our electrical network. I know it is the first week and too many lectures I'm uploading, but these 3 lectures actually will have the review class in the next week. And I'll also try to restrict myself to this article only for this particular class. So to obtain the transfer function of the electrical network, basically we have 3 basic passive components. These are capacitor, resistor, and inductor. They are corresponding voltage current relationship, current voltage relationship, as well as voltage charge relationship. All these are actually summarized in this table. This is actually our table 2.3. So this is our table 2.3. So we already know most of the thing. As well as their impedance, how to calculate the impedance and the admittance. So corresponding values are given. So if an electrical network is given, as we already said, that from schematic diagram to obtain the transfer function, basically we have to transfer function, we have to apply the physical laws, fundamental physical laws, and for electrical, those are actually Ohm's law and your Kirchhoff's current voltage law. So basically, the analysis that you have studied in the first year, mesh analysis, nodal analysis, these sort of simple ideas we actually have to adopt to figure out the transfer function of the electrical network. So let's start with the network. Say we will start with a basic RLC circuit. So start with here. Say we have a basic RLC circuit. An inductor, then you have a resistor, and then you have a capacitor. Okay, so say all these are time varying components, so small letter values. Then you have L, R, these are the passive components. And actually you have to find out the voltage across the capacitor, which is VCT. And you have to find out the relation. Output is your VCT, this is your output, and this is your input. So you have to find out the relationship. So since there is only one loop, so there will be only one current flowing. So assume that current is IT. So if we apply the Kirchhoff's voltage law, so the summation of the voltage along the path has to be equal to 0, or basically the other way to represent it is the voltage consumption should be equal to the voltage supplied. So there is only one voltage source. So all the voltage consumption in the passive component will be equal to the source voltage. So L dit by dt, which is the voltage across the inductor. So from here you can see that. Then plus We have voltage across the resistor, so that is R IT plus 1 by C 0 to tau. Tau is just an integral operator, so I tau d tau. Okay, so the voltage across the capacitor, and that should be equal to your supply voltage. So basically, the operator will be in the integration, but limit has to be the current. Limit has to be the time itself. So basically, we are measuring the time from 0 to t. Okay, so this is how you have to find out the relationship, and based on that relationship, basically, what you can find is now you have a differential equation. So, but you have an integrator as well. So nothing to worry about the integration. You can also apply the integration as well. So integration can be also converted into the Laplace domain. But now what we have is in the other side, you have the input parameter. So in this side, you have input parameter. So what we know is so far from the differential equation that in one side, you should have the output parameters, and in the other side, you should have the input parameter. So in this case, a simple input. So to bring the output into the other side, so basically, we can actually replace the current by charge. Because the voltage across the capacitor is actually related to charge. So this is what it means. We can actually write Qt equal to CVCT. Okay, so that is where how we can bring the VCT. So before that, we actually have to bring the uh, charge into that equation. So for that, actually, you can take the help of this column. Okay. So I is actually, we know that current IT can be represented as dq by dt. So dqt by dt. So I can be replaced by dq by dt. So what we are going to get here out of there, this equation is L d square qt by dt square plus r dqt by dt plus the accumulation of the current is nothing but charge, so 1 by c qt equal to vt. Okay, so you all the terms here is now in terms of the charge q, and now q can easily be replaced by c vc. So if you replace it, then what you're going to get is L, C is a constant, so L C d square VCT by dt square plus RC dVCT by dt plus actually it will be if you replace C will be cancelling each other, so VCT equal to VT. Okay, now as you can see, in one side you have all the output parameter, which is VCT, and in the other side you have the input parameter, which is VT. Now you can easily, now we have the differential equation. So if all the initial conditions can be assumed zero, because no initial value is mentioned, so in that case we can say that we can take the Laplace transformation, and the Laplace transformation will give us LC, because of the fact that we have a second order, so it will be S square VCS capital, because in the Laplace domain all the parameter will be capital letter, then plus RC first order, so RCS VCS plus VCS should be equal to VS. So just take common, now it is a algebraic equation, so LCS square plus RCS plus 1 VCS equal to VS. So our transfer function is basically output by input. So basically VCS by VS equal to 1 by LCS square plus RCS plus 1. So in general, we don't want to keep any coefficient of the highest order of the S. So you can take common. So if you take common of 1 by LC, then what you are going to get is 1 by LC in the numerator, and in the denominator S square plus R by LS, R by LS plus 1 by LC. So this is your transfer function G of S equal to VCS by VS. So any other parameter can also be given as output, and correspondingly you actually have to find out the relationship between them. So this is the way to do it, very simple, applying Ohm's law, and as well as in case of the mesh or loop, basically you have to apply the Kirchhoff's voltage law to find out the summation of the voltage in the loop, and it should be equal to 0. So to make it more generalized and more easy to deal with, what we can do is actually we can adopt a policy like you know what is the voltage across the capacitor. So voltage across the capacitor, if we try to find out in the Laplace domain, so voltage across the capacitor is nothing but the impedance into the current. So impedance is 1 by CS or SC into the current, that is 1 by S. So all in the time domain. So this is for the capacitor. Okay. So similarly for the inductor, the voltage across the inductor should be equal to impedance. Impedance is LS, is voltage across the impedance of the inductor into the current. Okay. So this is for inductor. Similarly, for the resistor is the simplest one. So basically, we are assuming that R is a constant, but R is also can be dependent on some parameter like temperature. But we're just assuming these are linear parameters, constant values. So this is true for your resistance. Okay, resistor maybe. Okay, now instead of deriving the differential equation, is there a direct way to go for the transfer function of the electrical network? That is what we also try to see. So if you are given a electrical network, say we are given something like this, the previous one, don't worry, the previous network, inductor, then you have the resistor, then you have the capacitor. So this is your VT, this is your LRC, obviously, then you have VCT. Okay, so is there any easier way? Condition provided that we already know the voltage across there. So there, yes, definitely there is an easier way. So what we can do is actually, instead of writing their parameter values, our LC will be representing their impedance value. So say impedance value maybe ZL. This is your ZR, and also this is maybe ZC. So, and also this, all the parameters that we are giving in the time domain. So we will also give their corresponding Laplace domain parameters, like here you have current IT. So what we are going to do here is actually we'll give the inductor in terms of their impedance. Then you have the capacitor, then the resistor and the capacitor, as well as your voltage source. So as well as your current in the loop. So current will be IS, voltage will be VS, voltage across this one will be VCS, as well as this will be your, what is impedance? Impedance is basically LS, and this is simply R, and this is 1 by CS. Okay, so once we know that, then we can say that summation of all the impedance multiplied by the current is actually going to give us the source voltage. So we can easily write something like this, LS plus R plus 1 by CS into current IS should be equal to your VS. So for simplification of writing, you can also adopt this formula. So what is the bottom line? Bottom line is, in a single loop, what we are finding is summation of sum of impedances, sum of impedances is actually multiplied with the current of that corresponding loop. That will give you equal to source voltage. It may or may not, a loop may or may not have a source voltage. If it doesn't have a source voltage, then it will be a zero simply. Okay, so this is how, even without going, so there is two ways. You can always go for the differential equation, then convert the differential equation using the Laplace transformation and find out the corresponding transfer function, or directly convert the circuit parameters like LRC into their corresponding impedance, and the voltage and the current also into the Laplace domain, and then just simply applying the summation of the impedance into the current in the loop, you can find out the voltage of that loop. So idea is very, very simple. Okay, so now we have seen the thing in terms of actually the mesh analysis for a single loop. So you can also apply the same thing in case of nodal analysis. So in case of the nodal analysis, if you think that you have two nodes, you have one node here, which is the voltage is Vs, and you have another low node here where you have the voltage VCS, then can we apply the nodal analysis here? So basically, if you write for VCS node, then what you can write is VCS minus Vs divided by the total impedance. So total impedance here is basically this two. So basically R plus LS plus VCS divided by the impedance, this one. So 1 by CS. So the total summation of the total current in the node must be equal to 0. So simple. So you can also go for nodal or mesh analysis, whatever you like. And the third approach to the same problem can be using the voltage divider rule. So using that was nodal. So that was nodal. And also you can go for voltage divider. Okay, so we have one impedance. This one is your Z2S, and this is your Z1S. So So voltage across the VCS will be actually Z2S divided by Z1S plus Z2S into Vs. So very simple thing. So you don't have to worry about either of the method. There is three options you have for this one. It can be you can apply the mesh or loop analysis. You can also apply the nodal analysis, or you can also go for voltage divider. Which one you like, you can go for that. Now let us take one example. Example 2.10, multiple loop. So if you have multiple loop, then how to deal with the thing. So these are again simple examples. We'll try to do some complex example in the later classes. In the beginning class, this is first week, so you're always doing the simple things. So in this case, you actually have two loops. So in the first loop, you have a resistor and the inductor. In the second loop, you have one inductor, one resistor, and one capacitor. Okay, so they have given R1, this is R1, this is R2, this is your L, and this is your C, this is your the VCT, which is your output, and now they have given you the input as well, VT. You have two currents in the two loops, so this is your I1T and this is your I2T. So as before, as you know from the first year, you have your own choice of choosing the current direction. So if you see after whatever the direction you have chosen, if your current is giving a negative value, that means actually you have to change the direction after the solution. Okay, so now what is the first step? First step is very simple. First step is to convert this one, all the parameters of the circuit into the Laplace domain. So let us change that. So I'm taking help of a different color. So R is remaining as it is. No changes in that. So this one will be actually I1S. This one will be I2S. Inductor. For the inductor, you just multiply with an S. So this is now converting to impedance. For the capacitor, you have to write 1 by CS. This one is now capital VS. And this is capital VCS. So first step is just rewrite everything in terms of Laplace. Then you have to write two equations, one equation for the loop 1 and the other equation for the loop 2. Okay. So how to do it? The basic idea is as before. So what you have to do is the summation of the voltage. You start with the resistor. So R1 I1S plus the voltage in this current in this inductor will have actually 2 I1 minus I2. Once you are considering the first one, then it has to be I1 which should be positive and I2 should be negative. So I1 minus I2. So you write that plus I1S. It's better to write it follow the same principle. So LS I1S minus LS I2S should be equal to your VS. Okay, so in the second loop, the current will be actually two current will be there for the inductor as well. So now this time it will be minus of that current, minus of the first current. So uh, uh, we can write in this way: I1, I2 minus I1 this time. So I2 will be minus. So minus LS I1S. Then you have plus LS I2S. I2 is positive now. Then you have a drop across the R2, so plus R2 I2S, and plus you have 1 by CS I2S. There is no voltage source, so it should be equal to 0. Okay, so now you can have two columns. You have to find out the coefficients of I1 and I2, organize them. Then you have to apply the Kramer's rule or any other suitable one from your circuit analysis you can choose. So basically, you can write something like this: R1 plus LS I1S minus LS I2S equal to Vs. Then here you have minus LS I1S. Then all the impedances will be summed together. Basically LS plus R2 plus 1 by CS with your I2S equal to 0. Now if you apply the Kramer's rule, then what you are going to get is, you can also find out what will be I1. You can also find what will be I2. So you have to apply the formula like this. So for the I1, these values will be replaced by this column. So Vs by Vs 0. Then you have minus LS. Then you have plus LS plus R2 plus 1 by CS. Okay, and divided by del. What is del? Del is the determinant of that, of the coefficients of I1 and I2. So similarly, if you want to find I2, then you have to replace this column by this column. So basically, what you have now, R1 by R1 plus LS divided by minus LS. Okay, so then you have Vs, then you have 0, then you have the determinant. So this will give you I1 and I2. Now, which one I need? Because we need, basically, we want to have our output is actually VCS. So for that, we need actually I2. I2S times the impedance, that is 1 by CS, is our result. So we need this one. So you just apply the formula. One thing, you just, if you don't get confused, your del is nothing but your R1 plus LS and minus LS LS plus R2 plus 1 by CS. Okay, so basically this is first year thing you should already know, but just because of the first week we are going, this is just a review, I think, and also I'm not sure whether you have done it in the Laplace domain or not. So we are doing things now in Laplace domain. Okay, so you can find out the corresponding transfer function. So I'm leaving it to you. So your task is to find out what is G of S equal to VCS by Vs. Not necessary, it is always has to be the voltage across the capacitor. They can also ask you to find out something like this as a transfer function, I2S by Vs, or it can also be I1S by Vs. Okay, so this can be your alternatives they may ask you to figure out. So the procedure is same. So correspondingly, you figure out what are the things that you have to do. So now, similarly, also you can apply your nodal analysis to solve this one, the same problem. You can apply the nodal analysis to solve this one. In this case, you will have two nodes now. Basically, you have to take one node as this node. You can take as a VL maybe. Okay, so this one is a VC already we have, VCS. So you can just apply two equations. Previously we solved it by one equation. Now you are going to solve it by two equations. And also for the nodal analysis, as you know, that it will be helpful to apply in admittance instead of the impedance. So you can also use the admittance Y, then admittance times the voltage, summation of that will be equal to your current in the other side. So you can apply that thing as well. So this is actually your example 2.11, example 2.11. So do it by yourself. It is already worked out. So go for that one. As well as with the current source, if you want to see one example with the current source, then actually you can also go for example, I think you should go for example 2.12. So all these are worked out example and the same principle they're following. In case of the mesh analysis, what you do, summation of the impedances into current, they're equal to voltage. Now for the nodal analysis, what do you do? Summation of the admittances into the voltage should equal to the current in the node. So maybe summation of the currents in the node if you have a current source. Okay, so go with example 2.12. That will help you clarify your previous knowledge. Just review. I'm not going to in detail of that one. Okay, so go for three loop exercise if you want to go for, and then you have your example 2.13. So three loop, and also actually they are given using their physical quantities now. So physical quantities. So they are giving this is capacitor, this is resistor, then you have an inductor. Okay, so then you have resistor again, then you have inductor. Here as well you have another inductor. So my voltage source. Okay, so this parameter is given 1 by S. This is 1, resistor value is 1. Then you have 4S, and you have 3S, and this one is also 1, as well as this one is twice S. Then you have, they have given VS, this is your loop 1, I1S. This is your loop 2, I2S, and this is your loop 3. Okay, so loop 3, I3S. So how to solve it? So loop, we know that summation of the impedances with the first one, then the summation of the common impedances with this second one and the third one, and then the supply voltage. Let's try to see what I am saying. So here I1 current is going through all of them, but to this one and this one I2 current is involved, and for this one I3 current is involved. So what I am trying to say is all the impedances of the first loop will be there. So all the impedances are actually, we have two resistors, so summation of those two is 2, 1 plus 1. Then you have 2s, so all these are interacting with current 1, I1. Then with the I2, and also it has to be positive because we are considering the loop 1. So these two components are actually interacting with the I2, and it has to be negative. So negative I2, or write the summation of the impedance first. So you will have basically 1 plus 2s, or actually the other way around will be better, be twice s plus 1. Then you have I2s, and then I3 is related to only this one, so you can just write I3s should be equal to your Vs. So this is your loop 1, the equation for the loop 1. Summation of all the impedances of that loop and that current of that corresponding loop. So whatever the common impedance in between the loop 1 and loop 2, then the current of the loop 2, and what is the common impedance of loop 1 and loop 3, which is 1, and that current. So similarly, if you want to find out for the loop 2, then what should be the value? Only now this one will be positive, the other two has to be negative. So what is the total impedance of the loop 3? Loop 3, we have 5s, basically 2, 3, 5, then 4, 9s. So as I said, 9s plus 1 resistance, then it is your I2s. So what is common in between 1 and 2? 1 and 2 is basically twice s plus 1, I1s, and that has to be negative. And then you should have current. What is common in between? That one is also negative. In between 2 and 3, that is 4s, I3s. And there is no voltage source, so this should be the thing. Okay, similarly, for the third loop, what is the total impedance of the third loop? Third loop is basically 4s plus 1 by s. That current has to be positive. So, okay, so that current has to be positive with I3s. Then common in between 2 and 3 is 4s. 4s, that has to be negative, 4s, I2s. And common in between 3 and 1, so basically is only the resistance with magnitude 1, so minus I1s. Okay, so now you have the equation. So actually the problem I wanted you to write the equations, nothing else. So this is our answer, but as you have seen, the things are not that complicated. So basically impedance of the loop and that corresponding current, multiplication of that current, then you have the common impedance of the adjacent loop and the current of the adjacent loop, and then you should be equal to your voltage source. So one thing we just missed here, there is no voltage source here as well, so it should be 0. So if they ask you to find out what is our transfer function, say they are giving transfer function equal to I3s by your Vs. So it should not be that difficult. You have to apply the Kramer rules. Now you have 3 columns instead of 2 columns. So maybe the calculation will take more time, but you will be able to find out what are the corresponding transfer function. Okay, so this is electrical network, series parallel networks using our passive component, RLC. One of the important component that we should cover is also the op-amp. So Op-amp is also included here. Operational amplifier, that is why it is op-amp. And what happens? What are the properties of the op-amps? I think you have learned this in electronics too in the third semester. So we are not going to detail of any one of the component. Rather, we will just exploit their characteristics. So what are the characteristics of the op-amp? Op-amp have two input. We call differential input. One is the negative, one is the positive, and we call, say, this is your plus V1T, and this is your plus V2T, V2T. And you have to have give two bias voltage, so plus V minus V. In general, plus 15 minus 15. Then you have V02 is output. So what are the properties of the op-amp? The properties of the op-amp is, first of all, their input is differential. So number one is differential input, and that is your input is V2T minus V1T. So this is your differential input, number one. Number two is very high input impedance. So high input impedance, impedance. So Z in is, ideally we call it infinite, so that no current is actually flowing inside the device. And then you have a very low output impedance, so low output impedance. So Z0 is actually 0. Okay, so ideal. All these, what we're saying here is ideal case. And a very high constant gain, amplification gain. So for, gain is very high. So your high constant gain. So ideally, the gain is infinite. Okay, so these are the common properties, and based on these properties, if you try to find out what will be your output, V0T is A times the input, the differential input, that is V2T minus V1T. So this is your characteristic of the op-amp, ideal characteristic. So as you can recall that op-amp operate in two modes. One is inverting, one is non-inverting. So we start with using the inverting one first, reviewing the inverting one first. So inverting operational amplifier. So op-amp. So look at the circuit diagram first, then we'll try to find out the equation. So we have something like this, and now actually we are applying the feedback here. So non-inverting input will be there. Then you will have two resistors. So the inverting, non-inverting one is grounded, so plus one is grounded. So voltage source is connected with okay, so we are calling this one as a Z1 S, and we're calling this one as a Z2S. So even though we are saying resistance, showing resistance, but actually these are not resistance. Maybe block diagram should have been, box should have been a better idea to give, but okay, so this is how it is. Now also we are assuming that one current is flowing in this way. So I1S, and the other current is flowing, say, because, coming from this direction, that is your I2S.
Okay, so what should be your output?
The output is V0 according to the previous one, V0, V0T, equal to this time your V2T is actually grounded, isn't it? V2T here, V2T, V2T is grounded. So minus a V1T should be your output. So let us try to find out the effect of this feedback Z1 and Z2, how it is actually affecting our gain. Previously we had a very high gain, okay? So now how that gain will be changing because of this feedback. So let us try to see that. So as you know that input impedance is very high here. So there will be no current flowing. So any current, you say we are assuming I, S, something like this. So that has to be equal to 0 because ideally we said that Zi is infinite. So because of infinite impedance, there will be no current. So whatever the current flowing here should be actually same as current coming from this one. So what you can say that I1S should actually be equal to minus I2S. Okay, so in that case also there is called virtually shorted. So this node and this node is also known as virtually shorted. So if this is grounded, this can also be assumed grounded. So the current I1 can be figured out that from the voltage source going to the ground. Okay, so you can write VIS by the impedance Z1S. Similarly, in the other way, so this is your voltage and this is your ground again. Okay, so voltage divided by the impedance should give you the current. So V0S by Z2S should give you the current. So you know that output V0S by VIS is your actually your transfer function. So that will give you minus Z2S by Z1S. So basically this impedance divided by this one will give you now the gain or corresponding transfer function. So this will be the transfer function of the open G of S. So let us look at a practical example. Example 2.14. So you have one parallel network here, one capacitor and one resistor as a Z1. So whole thing is actually a Z1. Then you have, say this is your op-amp. So in the feedback, you have a series network, one resistance and one capacitor. Okay, so this is your V0S, this is your VIS, and this is your virtually shorted or V2, basically the non-inverting input, and this is your inverting input. And their corresponding values also are provided. So this is actually 5.6 microfarad. This is 360 kilo ohms. Here as well, it's 220 kilo ohms and 0.1 microfarad. So what they want to figure out is your transfer function, that is V0S by VIS. This is what you have to find out, and you already know what is the formula. Formula is minus Z2 by Z1. So what is Z1? You can also find out as a impedance, 1 by impedance. So the conductances, since parallel, they can be added together. So basically 5.6 into 10 to the power minus 6 into S, the in the admittance of your basically susceptance of your capacitor. Then you have to add the conductance 1 by R. So basically 360 into 10 to the power 3. All right, so if you simplify, then what you are going to get is 360 into 10 to the power 3 divided by 2.016 S plus 1. Just putting the value and doing the calculation. So similarly, what will be our Z2? Z2 is straightforward because of the fact that it is directly the impedances you can calculate. So it will be 220 R2S plus 1 by C2S is basically 220 into 10 to the power 3 plus 0.1. So if you just take it into the numerator, then it will be 10 to the power 7 by S. Okay. So Z1, Z2 is calculated. Now just put both the value here and manipulate a bit, and what you're going to get is minus 1.232 S square plus 45.95 S plus 22.55 divided by S. Okay, so this is your transfer function of the of the inverting amplifier, and this is also basically this equation is nothing but the transfer function of a PID controller. So how that is PID controller? This will be discussed in detail in your chapter 9. So before that, I think we should not focus on that. Those are actually advanced content. So we'll be trying to discuss more in detail in chapter 9. Okay, so next thing is a non-inverting amplifier. So non-inverting amplifier or non-inverting amplifier, how we are going to deal with it. So let us draw the diagram first for the non-inverting amplifier. We are applying the input here, the non-input, so VIS, but the feedback is still on the same path. So basically you have Z2S here, Z2S, and you have Z1, Z1S here. This V0S. Okay, so we can term this one as V1S, this node. Okay. So what will be our output? Our output by definition, V0S is actually A into non-inverting one, that is VIS, minus the voltage across the inverting one, which is V1S. So this is our formula by default. Now, what is V1S? V1 is actually, you have to apply the voltage divider. So if you apply the voltage divider, so then what we can get here is V1S is V1S can be written as Z1S divided by Z1S divided by Z1s plus Z2s into V0s. So if you just put the value here, so A, then you have VIS minus Z1s divided by Z1s plus Z2s, and then you have V0s. So in the both side you have V0s. So we can take them in the same side. We can rearrange a bit. Then what we are going to get is V0s. If you take common of it, then we have something like this. 1 plus, because in the other side is minus, so if we go into the other side, it will be plus A Z1s divided by Z1s plus Z2s should be equal to A VIS. Okay, so what will be our transfer function then? The transfer function G of S is nothing but V0s by VIS. So we can say that it will be basically A divided by the whole thing. So A divided by 1 plus A Z1s divided by Z1s plus Z2s. So it is slightly complicated, and also one factor is that the magnitude of A, which is open loop gain, is ideally infinity, so very, very high. So what you can do, both the numerator and the denominator can be divided by A. So we have 1 divided by 1 by A plus Z1s divided by Z1s plus Z2s. So this is what the approximation we talked about. So sometimes we have to apply the approximation so that we can simplify our calculation. So now if you apply A equal to infinity, then what we are going to get here is basically 1 by Z1s divided by Z1s plus Z2s. So for the simplification gives you Z1s plus Z2s divided by Z1s. Okay, so finally your transfer function G of S equal to V0s by VIS will be 1 plus Z2s by Z1s. Okay, so as you see that this factor is remaining almost same. In the previous one as well, we have seen that negative of this parameter. But for the non-inverting case, you have 1 plus Z2 by Z1. So one corresponding formula example is there. Example example 2.15. So you are given a non-inverting inverting open with this particular Z1 and Z2. So feedback is still on the negative side, then your VIS is here, and you have a RC network here, series network, and you have a feedback network here. Parallel feedback network, so that can go there. So visuals. So this time actually you are not provided with any real value, rather they have given you R1 C1 and R2 C2. So your task is to figure out what should be the corresponding transfer function, that is G of S equal to V0S by VIS. Okay, so how to do it? Very simple idea. So again, 1 plus Z2 by Z1. So calculate the Z1 and Z2. So in terms of symbolic values, so Z1 is a series network. So Z1S is simply R1 by R1 plus 1 by C1S, and Z2S equal to, we can also multiply to find out the equivalent uh, impedance. So R2 into 1 by C2S divided by R2 plus 1 by C2S. Not necessarily you have to go for the admittance. This is one way to do it, and this is that was one way to do it, and this is another one. So basically, you can apply any method you want from your first year courses to figure out. Then you just replace the value, and then you will get the corresponding transfer function that we're looking for. So this article 2.4, which is the transfer function of the electrical networks, will actually start with your, end with your last skill assessment exercise, skill assessment exercise 2.6. And here you have a network given. You have to find out the corresponding transfer function. So you have some real parameter is given. Okay, so you have inductor here as well as here, and then you have a voltage source here. Okay, so you have given Vt, the inductor here is 1 Henry, this is 1 ohms, then you have 1 ohms as well, this is 1 Henry, all the parameters are actually 1, and you have to find out the voltage across VL, this one, the voltage across the inductor VLs. So the target is to find out GS equal to VLS by PS. Okay, so how to solve it? Very simple. You have 3 loop. You have to assume 3 current. So the way to solve it is you assume 3 current, I1S maybe. Then you have I2S. Then you have I3S. You convert all this into impedance. So if your impedance LS, so basically it will be S. This ohms will not be changing. This one will be also S. This one will be also S. And replace this one with VS. Replace this one with VLS. Now you write 3 equations. So first loop, for the first loop, what we have is S plus 1, S plus 1 I1S. What is common in between two is S, so minus S I2S. Then you have what is common in between 1 and 3 is minus I3S equal to your VS. So second equation I2S. So what is common in between? S is common. So S I1S. Since we are dealing with the second loop, a negative sign has to be there. Then you have summation of all the current, all the impedances. So basically you have 2 inductor, and 1 capacitor. So we have to write twice S plus 1 with I2S. And what is in common in between 2 and 3 is basically 1 resistance. So we can write I2, I3, negative I3 is equal to 0. Okay. So what about the loop 3? For the loop 3, What is common in between 1 and 3? We already know that is 1. So 1 minus 1 by minus I1 S. What is common in between 2 and 3 is also one resistance. So it will be minus I2S. And then you have the total impedance of the third loop. So basically S plus 2 I3S. So what do you have to figure out? The voltage across the inductor. So for the voltage across that particular inductor, we have to actually go for the current I2. So what do you have to do? You have to find out current I2. So find out the current I2 using the Cramer's rule. Okay, so divided by del. And after doing that, what should be your output? VLS should be equal to S times I2S. So if you solve that, then you are going to see that your V input voltage will be appearing in this side, So then you find out VLS by Vs, and finally what you are going to get is S square plus twice S plus 1 divided by S square plus 5S plus 2. So I have given you the idea how to do it. So do the calculation by yourself. Do it yourself. Okay, so this is the end of this article. So in the next class, we will be covering the article 2.5, which deals with translational mechanical system transfer function. Okay, so translational mechanical system transfer function. Translation means basically the linear movement. So linear movement. So those systems, those gives linear movement, will deal with that one. So that will be inshallah our next topic in the next week. So see you in the next class, inshallah.